To the third problem in recursion problem set. So here it says, write a C program which takes an integer n and prints out the Sierpinski's triangle with n pixels width and n pixels height. And note, you can assume that n can be written as 2 to the m, where m is a natural integer. And basically, these are three examples of a triangle, Sierpinski's triangle, with 2, 4, and 8 respectively as n. So here, for example, if I give you 2, then you have to print a black pixel on the top left, a black pixel on the top right, and a black pixel on the bottom left, and a white pixel on the bottom right. So the triangle, so basically the triangle has 2 as the number of pixels. So 2 pixels here and 2 pixels here. And if it's 4, so we have 4 pixels here, 4 pixels here. So basically it's a matrix. It's like a rectangle, a square, where the size of that square is equals to n. So that's 4, 4. This is 8, 8 for n equals 8. And here's the general art of the triangle. So for a very, very large n, we get some art like this. And basically, so here's how we're asked to print the output. So here it says, for the sample input 8, for this triangle here, we want the output to be formatted like this. So a bunch of hashtags, H hashtags, and spaces. So hashtag, 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 and space, and so on. So basically that's it. So we can see that this problem here is recursive in nature. It's very, very, very recursive. And you're going to see that in a bit. So basically, if you look to this part over here, let's put in a black ink here. So this triangle, so this triangle has 3 parts. It has a black triangle. Let's change the color. A black triangle, another black triangle, another black triangle, and a white triangle, which is the same for this bigger triangle. So there's a black one on the left, a black one on the bottom left, and a white one on the bottom right, which is the same thing for smaller triangles like this one, for example. So there's a black on the top left, black on the top right, black on the bottom left, and white on the bottom right. So basically, if we call the function with n equals 8, so f of n, if f of n equals 8, then the function has, let's make it 8, then we're going to talk in more general way later. So if we call it with f of 8, it has to divide the problem into smaller subproblems where the size of n would be 4. So f of 4, and here f of 4, and f of 4, and f of 4, where this first 4 is the first top left rectangle, the top left square, top right square, bottom left square, and bottom right square, which is the same thing here. So f of 4 will call f of 2, f of 2, and f of 2, and so on. So you can see that the size of the problem is dividing every time. So we can create a function called f, for example, that takes the size of the rectangle, so that's n, and it also takes the beginning of our rectangle. You know what, let's get rid of the n, let's just give it the beginning, so the beginning of the rows. So the first row is, let's call it big I, which stands for the index of the beginning of the rows, and the rectangle last row is basically going to be something like and I, and the first column would be something like beg j, and the last column would be something like and j. So by these four informations here, these four numbers, we would be able to identify which sub-rectangle we're talking about from this space here. So if I tell you, for example, I'm talking about this full rectangle, then these four numbers would be something like this, something like F0, the end I is 7, that's index number 7, so 0 up to 7, and then the beginning of j is 0 and the end of j is 7. So by supplying these four arguments, it translates that we're talking about this entire rectangle. If we, for example, are talking about this sub-rectangle here, then we have to call the function with ff. So the first row would be 0, the last row would be 3, so this one here, that's 3. And the first column would be 4, so that's 3 plus 1, so this one is at index 4. And the last column is 7. So you can see here that the row is the same, the beginning of the row is the same. Here the end of the row is not the same, it's basically the beginning plus the end divided by 2, so that's 0 plus 7, we get 7, we divide that by 2 and we get 3. There is no, we don't take the remainder, of course. And from here we have same thing here, so the 7 remains the 7, and then the 4 is 7 plus 0 divided by 2 plus 1, because we have to take the index just next to the one we're talking about. So let's write a real function now. So our function f takes beg I, and beg j, and j. And basically, what is the base case? The base case is that if n equals 1. If n equals 1, then all we have to do is, well, we just have to print a black pixel. We have to print a hashtag. So let's do that. So we're going to print, so if the beginning equals, the beginning of I equals the end of I, or the beginning of j equals the end of j, well, in that case, we're just going to print a hashtag. Okay? Otherwise, we're going to have to call 3 different subproblems. The first one, we're going to call f with the first I, which is the same I, so that's beg I. And for the end I is going to be the size, so the beginning plus the end divided by 2 to get this one here. So that's beg I plus end I divided by 2. And the same thing here for j. So j, the beginning of j is basically beg j, same as its parent. And the last element would be the end j plus the beg j divided by 2, so this one. So that's beg j plus end j divided by 2. So this is the first subproblem. this subproblem will deal with the top left square. It's the same thing if you want to do it with the top right square and bottom left square. The only thing that we have to change is the indices here. So we have to call, for example, for the bottom left square, f of, so the beginning is basically is going to be the beginning I plus the end I divided by 2 plus 1. So beg I plus end I all divided by 2 plus 1. And well, that plus 1 is, you can omit that, so that's not required because it's a recursive function. We're going to test that later to make sure that you can omit it. And the same thing for j here. So for this subsquare, the beginning of j of the new square is the same as its parent, so that's big j, but the end of j is equals to the big of j plus the end of j, so this one here plus this one here divided by 2 to get this one. So big j plus end j all divided by 2. And the same thing for the third square, but we're gonna just code that directly into C because I guess you got the idea. So basically we're calling the same subproblems 3 times for the top left, the top right, the bottom left.